In this video, we're going to take a look at some applications of heat engines and their properties. So this first one is a PV diagram from a conceptual point of view. So we have pressure up here and volume here. And you'll see the terms pressure volume diagram for a typical four-stroke ICE, internal combustion engine. It's your car, unless you have an electric vehicle. And so four strokes altogether. Let's see if we can count them. So if we look at the arrows, we have to pick some place to start. So here's A, then to B. So what is A to B? So we see a point right here, and it says exhaust valve closed. And this is expansion. And right here it says intake valve open. So right before A, the intake valve open, exhaust valve closed. And now we see an expansion. And in this expansion, fuel is sucked into the cylinder. So A to B is intake. Then from B to C, we can see that I'm going to do this in a different color. This is a compression. So this is also called a compression stroke. And then right here, IGN stands for ignition. So B to C is compression / ignition. And then boom. So the peak pressure builds as the fuel burns. So there's a little bit of a time delay as the fuel burns, and that's when the peak pressure is created, and then we see an expansion happen. So from D to E, you can see an exhaust valve open. So this is our power stroke. And we know the area under the curve is the work done. But it took work to compress the fuel, and then we ignited it, and then it expanded. So this region between the two graphs is the net work done. So from C to D, let's just follow up on that. From C to D, we have consumption, fuel consumed, as the pressure builds to its maximum. And then D to E is our power stroke. So the green is the net work done. Then exhaust valve opens, and E to A is exhaust. Good. All right, so another practical example about where we use heat engines. But I think this is really the most interesting part, is that it takes energy. And so, you know, our engines are already running. So crankshaft is already spinning, and we have energy available to do this compression, and then it's ignition, so we get this incremental amount of work done. Right, so the compression stroke and the fuel stroke still shows that sort of inverse relationship between pressure and volume. And it does require energy to do the compression stroke, but we get a little bit extra out of it. And that's essentially where the efficiency comes into play. And that's also what this video is about too, is efficiency. So we'll take a look at some problems that involve efficiency. Okay. And again, I think a really important thing about this thermodynamics chapter is so much of it is about decoding the clues that are given to us. So here we go, heat engine does this much work. All right, so this is our work done. And then while absorbing 22 kcals, well, this is annoying that this is kcals and this is joules. And absorbing that much. And so this is QH. This is the heat that's been harvested from a high temperature reservoir, right? So we know, I really do like this diagram, is that when we harvest QH, we can divert some to doing useful work. And then we also are going to have to ditch the leftover somewhere. So the efficiency is really built into this diagram, that what we want to do is we want to get as much work as possible out of QH. So efficiency is going to be equal to work done over QH. But we're also recognizing the fact that QH is equal to the sum of the work we get plus what we have to waste. And we have to waste something, because if we don't have two different temperatures, hot and cold, then we don't get heat to flow in the first place. So that's the whole principle of heat engines: get heat to flow and then siphon off a little bit of energy to do useful work. So the work done is 9,200. Let's convert kilocalories into joules. So 22 kcals, and we'll multiply by 4,186. Okay. So that means that I'm going to have 9,200 over 92092. So 9,200 divided by the answer I just got. Yeah, that's not great, is it? So that's about 10% efficient. Looks like they want two significant digits for this. So that would be 0.10, which is equal to 10%. Okay, now, in our next problem, we take a look at the exhaust temperature of heat engine is 230 degrees Celsius. Well, that's a problem, so we're going to convert that. 230 plus 273. Okay, so 503 Kelvin. And what's the high temperature? The Carnot efficiency is going to be 28%. So Carnot efficiency is this. Remember that Carnot was a very special heat engine, because we go from an isothermic right, let's just sketch this out really quick. So we have an isotherm, then an adiabat, and then another isotherm, and an adiabat. There we go. So iso, and adiabat, where Q is equal to 0, and then Q is equal to 0 for this process also. Right, so so on the isotherm, that's when we are harvesting Q, and on this isotherm, that's where we're exhausting Q. And since it's an isotherm, then that means that this is going to be proportional to the temperature of our reservoir. And because of this proportionality, that's how come we can rewrite the efficiency. So if I was going to take this relation here and substitute in for work, so work is equal to QH minus QL. So I make this substitution, and then the efficiency can be written like this, where I've got QH minus QL all over QH. And of course, that cancels off and gives 1. So this is 1 minus QL over QH. And QL over QH is essentially, this is supposed to calculate efficiency, but this is the percent wasted. Now, because QH is proportional to TH and QL for this special kind of cycle, Carnot cycle, then we can rewrite the efficiency just in terms of temperatures. So it's a very good question. So 1 minus TL over TH. Okay, and now we can go ahead and we want the Carnot efficiency to be 28%, so this is 0.28. It's equal to 1 minus, and the high temperature is 503, so we're looking for TL. Great, so we rearrange this equation, and I have TL over 503, 503. And so I'm 1 minus 0.28, which is 0.72. Again, percent wasted. And, you know, again, as we're working through this problem, why do we, all these heat engines are so incredibly inefficient. Why do we use them in the first place? And the answer is, once again, is that the energy density is very high and it occurs in what we consider to be relative abundance. Fossil fuels, we consider them to be in relative abundance, but of course, that's a misguided notion. So anyway, there we go. And you could subtract out 273 if you wanted. To get the answer in degrees C. So 89 degrees Celsius. Okay, let's just try a couple more, and I think you'll find this really helpful on the quiz. I chose this one just because it's it has some different vocabulary in it. Let's start off by converting this into Kelvin. So this is 483 K. And 318. And the engine's power output is 950. Calculate the rate of heat output. Okay, so once again, we've got QH, but QH is proportional to the power, the rate at which we harvest energy. And then this is our output. Which is proportional to power, of course. So in a given, say in a given quantity of time. And then we have QL, which is proportional to the power that's wasted. Okay, so our power output, this is the one that is 950 watts. So calculate the rate of heat output. So this energy loss, this is heat wasted. So this is actually what we're looking for. Okay. Good. So let's start out by doing the efficiency. So 34%. I'm going to carry one more extra significant digit here. Okay, so that's our efficiency. And so that's the ratio 950 here. So this is equal to Q work done compared to QH. So the QH, which could be power harvested, right? Because I'm using energy and power interchangeably since it's sort of a per second concept. That means I'm going to take the work, which is 950, and divide by the efficiency, which is 0.342. Divided by the answer I got. Okay, 2781. And watts. And then so QH, or QL rather, per unit time is going to be equal to the difference between these two. So I'm harvesting at this rate, QH per unit time, and minus the work. So 2781 minus 950. Okay, 1831 watts. Yeah, right. Your car engine gets hot, doesn't it? All right, and then the last thing too, a heat engine utilizes a heat source at 550, has an ideal efficiency of 28, and then we want to increase the efficiency to 35%, so we need a different low temperature. So we need to solve for the low temperature first. So TH is going to be equal to 550 plus 273 to get into Kelvin, 823 K. And then what we want is an efficiency of 35%. And so what's the temperature of the heat source? So we're going to increase the heat source to a new value, but we'll need to solve for the low temperature first. So 0.28 equals 1 minus TL over 823. So TL equals, okay, great. Let's see what this looks like on our calculator. We're going to do 1 minus 0.28 to give us percent wasted. Then we're going to multiply by 823, and that gives us TL. So 593 K. And now what we want is 35%. So now we're going to solve for our new TH. So same thing, E equals 1 minus TL over TH. And we want it to be 35%, so that's 0.35. And the TL is 593. And that's what we're looking for. So 1 minus 0.35. And then we're going to divide that into 593. And so TH, the new TH, is equal to 912 Kelvin. And I suppose if you want, we could write that in degrees Celsius. It's probably what mastering physics would want. And looks like two significant figures. So this would be 640 degrees C. Okay, good. I hope you found this video helpful. Again, it's just a lot of new vocabulary, but conservation of energy is an old friend. And keep your eyes on the lookout. So for the quiz for this chapter, I'm definitely going to be using this diagram. Okay, good luck. And of course, email or text if you have questions.